So now in the third example, in case of electrophilic substitution, I will consider sulfonation of benzene. Sulfonation of benzene it is. Here benzene is treated with concentrated H2SO4 or with concentrated H2SO4 we take SO3 also. Combination of these two is H2S2O7. This is called oleum. So we can take here either concentrated H2SO4 or with concentrated H2SO4 sulfur trioxide gas is also passed there, and here we get benzene sulfonic acid. Benzene sulfonic acid and water as a byproduct. Here H2SO4 will also act as dehydrating agent, and this is an example of a reversible reaction. This reaction is reversible. On heating this one further, this will be lost and we get again benzene. That is also called ipso substitution in this case. If we consider here that is mechanism point of view, again here the three step. The first will be generation of electrophile, first step. In the second step, electrophile will attack benzene ring, that will be the slow step, and the final step will be removal of H. So the first step in the mechanism, it is generation of electrophile. So here H2SO4 loses a proton to give this one. In the second step, this H plus is going to attack H2SO4 another molecule, that is this H plus can target this point or this point. So we can write it like this. This is protonated sulfuric acid. Now water will be lost here, and we are having SO3H positive. This sulfonic acid group here act as electrophile now, or this H plus can attack this SO3 to give this one. So oleum is better to use, that is so here we can consider that is this proton to target this SO3. For example, this bond we can consider, and we have this one, or it can be written as like this also, SO3H, sulfonic acid group. This electrophile is going to target benzene ring in the second step. in the second step, this electrophile will pull this pi electron to generate carbocation. Now again it is resonance stabilized, so we can write in that way also, or we can directly in the next step consider here a removal of this H plus also. That is the actually it will be the part of third step. So before going to third step, we should again here consider its resonance stability. This is shifted here, positive charge on this point, SO3H, then this is shifted here, so positive charge on this point, now SO3H, and it's equivalent of these three, that is the Wheeling intermediate, SO3H, this is intermediate called Wheeling intermediate. Again, this is the slow step in this case. So here the rate will be depending on proportional to benzene and concentrated H2SO4 we have taken. So it will be like this. That is second order kinetics in this case. It will be observed second order kinetics. And the third step will be, we can consider any of these three structures. A removal of hydrogen will be there. So third step here, a removal of H and we can consider this species H is removed, and as a product we are getting here benzene sulfonic acid. This reaction is reversible as I told you in the beginning. So on heating further, this can be removed and H will be coming here. So this is also called ipso substitution. So this was the third example in the category of electrophilic substitution. In the next case, we will consider the fourth example, and that is called Friedel-Crafts reaction in this case. So the next example is here, Friedel-Crafts reaction. This is in two portions. One is alkylation, that is alkyl group is attached to the benzene ring, and another one is acylation. So two different examples we have in this case, alkylation and acylation. In case of Friedel-Crafts reaction, in both the cases, a requirement of Lewis acid is a must. So Friedel-Crafts reaction is applicable only in case of activating groups, not in deactivating groups. Even there is some limit in case of activating groups, we will discuss further both for this acylation and alkylation. So the first thing we are going to consider here, that is alkylation. Here we take benzene, alkyl halide, X can be Cl or Br, and Lewis acid catalyst like AlX3, AlCl3 or AlBr3. So in this case, we are getting alkyl benzene and HX as byproduct. Alkyl benzene will be product here. Again, if we consider from mechanism point of view, the first step will be generation of electrophile, and this carbon halogen bond will be broken by this AlX3. It will pull halide ion, and R plus, that is an electrophile, a carbocation, will get as an intermediate. If it is methyl group, then methyl carbocation. If it is ethyl group, then ethyl carbocation. If other group is there, and if chances of rearrangement is there, for example, 1,2 hydride shift or 1,2 alkyl shift, we will consider later on. So that will also be there. So the first case, in this case, the first portion in the mechanism, we are going to consider here generation of electrophile in this case. So first step, generation of electrophile. Here in this case, carbon halogen bond, R is alkyl group, it can be methyl, ethyl, anything. This Lewis acid catalyst will cause here heterolysis. So we have R plus carbocation and AlX4 negative. So the first step, we are getting here a carbocation as an electrophile, and this R plus is going to target benzene ring. Now this R can be different types of group, that is methyl, ethyl or propyl, etc. So I will consider those examples now. Suppose R is methyl, then, and say it is chlorine or X, AlX3. So we get here methyl, methylium ion, methyl carbocation, electrophile, and AlX4 minus. Similarly, if we have R is equal to ethyl here, again in this case, we have here ethyl carbocation as an intermediate, ethyl carbocation. If we have propyl group, so here in case as heterolysis will be there, heterolytic bond diffusion, AlX3. So CH3, CH2, CH2 positive and AlX4 negative. Now in the first two cases, there is no possibility of any rearrangement. But in the third case, we can observe this behavior. If this hydrogen along with the bond is shifted here, we will get a secondary carbocation. This is a primary carbocation. And if it is undergoing 1,2 hydride shift, hydride shift, then here it is converting into a secondary carbocation. Secondary carbocation is more stable than primary carbocation. So therefore, in this case, 1,2 hydride shift will be there. And with the benzene ring, this carbon will be attached, not this carbon. That is isopropyl group is this, so we will get here isopropyl benzene, not normal propyl benzene. In the first case, if we have methyl group, then methyl benzene. If we have ethyl group, then ethyl benzene will be there. But in this case, there is chances of, definitely fair chance of rearrangement because secondary carbocation is more stable. So isopropyl benzene will be getting. So in the second stage, this R plus, this electrophile either methylium ion or ethyl carbocation, or this will target the benzene ring. That is, for simplicity we can write here R plus only, here H is, this bond, pi bond will be shifting here, and we have this intermediate in this case. Again, this can be stabilized by resonance. And equivalent of these three will be this R, that is this Wheelan intermediate, and in the final step this removal of proton will be there. I can choose any one of these three, either this or this or this. And this ALX4 can be used here. ALX4. So product we are getting here alkyl benzene plus HX, and Lewis acid catalyst is regenerated. So the important thing is here in this case, we have to keep in mind, that is, if there is possibility of rearrangement, that is we are getting more stable carbocation, then definitely we should consider it. So many possibilities can be there by taking different examples. That is the important thing here. We keep this thing in mind. So that's all in this case, Friedel-Crafts alkylation. The important point is, wherever there is chances of rearrangement, we must consider, we should not forget it. The next example, now I am going to consider here the another, that is acylation. Friedel-Crafts acylation. FC, Friedel-Crafts ethylisation. So here we can consider benzene ring and acid chloride, for example, with anhydrous AlCl3. So acid chloride it is used here, or we can also consider acid anhydride. Acid chloride reacts very fast, and in this case it is mild condition, it is slow as compared to this. So preference is given to acid anhydride. Acid anhydride. And here we'll get acyl benzene, this is acyl group. Byproduct, it will be HCl, or if I consider this one, then the byproduct will be a carboxylic acid. So the product here, we have aromatic ketones in this case. Acyl benzene, it is here, acyl group is attacked. So alkyl aryl ketone in this case. Aromatic ketone we are getting in this case. If I consider that is the mechanism point of view, again the first step will be the generation of electrophile, and it will be then targeting in the second step benzene ring, and after that the third step will be removal of proton or hydrogen, we can say removal of H. That is the process of mechanism will be the same again in this case like earlier. So the next step here we have to consider this the mechanism step, and before going to that we can convert this product into alkyl benzene also. This can be converted, CO can be reduced to CH2 by using Wolff-Kishner reduction or Clemmensen reduction. For example, if it is treated with ZnHg and HCl, it will give us CH2R, and there is no chance of rearrangement in this case. So in the next step we can get here alkyl benzene. Now I am going to consider the mechanism for this step. The product I have written. In this section, mechanism section, the first step is here, that is generation of electrophile. So we can consider here acyl halide, AlCl3. This carbon chlorine bond will be broken, and we have here an electrophile called acylium and AlCl4 negative. If I consider acid anhydride, then again here we can target either this bond or this bond with this Lewis acid catalyst. If it is shifted here, then again here we have acylium ion and this RCO, O negative AlCl3. So acylium ion here we are getting as an electrophile in this case. The second step will be the attack of this electrophile on benzene ring. again, as we know here, it will target one CH bond is here, and this pi bond will be shifting, and this SiDm ion will be joined like this, and again it is resonance stabilized. So further it can be written as positive charge is shifting here, then the next step, this bond will be shifting here, and the equivalent of these three, this is called Wheelan intermediate. And in the final step, this hydrogen will be removed and the product will be getting. Third, and again this step, this is second step is slow. So rate determining step it will be depend on benzene, acid chloride or acid anhydride we have taken, and Lewis acid catalyst. So rate here will be proportional to benzene and acid chloride or acid anhydride and this catalyst. And the third step is here removal of H, and AlCl4 minus so aromatic ketone HCl and AlCl3, we are getting the final product in this case. As I told to you earlier, this carbonyl group can be reduced by using ZnHCl, amalgamated zinc. This is called Clemenson reduction. That is CH2 or Wolff-Kishner reduction. In this case, reagent is NH2NH2, glycol and KOH. So this is Clemenson reduction and this is Wolff-Kishner reduction, and we can reduce this carbonyl group. So that's all in this case, that is Friedel-Crafts alkylation and acylation. It has certain limitations, that is this FC reaction, FC Friedel-Crafts reaction works only for ortho and para-directing groups. Directing groups, not for M directing groups. Not for meta-directing groups like aldehyde group, ketone group, carboxylic group, etc. It can work only for. And even in ortho para-directing groups, if groups are highly activating, then this will not work. If mild activating groups are there, in that case it can work. So it cannot work if O and P group, P directing groups are very strongly activating, For example, NH2, O minus, OH, etc. Because these groups will be combining with Lewis acid catalyst because it is electron deficient. So therefore, because it can act as here Lewis base, so AlCl3 will combine with it, and in that case AlCl3 will not be able to generate electrophile as it was doing in the first step. So Friedel-Crafts reaction has these certain limitations, that is, it can be applicable only for ortho and para-directing groups, and even in that case, if very strongly activating groups like this are there, then it is not applicable, and it will not work for meta-directing groups. Meta-directing groups, for example, carbonyl groups, aldehyde ketones, cyanides, nitro groups, acid, carboxylic acid and its derivatives. So it will not be applicable in those cases. So that's all in Friedel-Crafts alkylation, acylation, and the last example I had considered in case of electrophilic substitution reaction.